So good morning and welcome back. Today we will further develop some technology, but along the way we'll also collect a number of interesting results. The two most important ones are first the Whitney embedding theorems, which clarify whether there is really a difference between the intrinsic definition of a manifold and especially its tangent spaces and so on, and the extrinsic definition, which we didn't follow, but which I hinted at, that you think of the manifold as being embedded in a higher dimensional Rn, and then that you construct the tangent spaces as planes in this higher embedding space. And I argued for the intrinsic point of view, because simply for physics later on, especially if the manifold is supposed to represent the universe, it'd be rather, well, funny to think of an even bigger space into which the universe is embedded. It's aesthetically not so fine. So we followed the intrinsic approach, but the question remains, maybe something could be gained by taking the embedding approach. And the Whitney embedding theorems tell you, no, they're equivalent. Okay, so that's good news. So we'll collect that result along the way. But then for further, so we will remain to hold the intrinsic point of view. And then we will go on to develop one key point, and probably only next time we'll then look at the full implications, namely that we will define vector fields, but we will find that the space of all vector fields is not a vector space. The space of all vectors was a vector space, but the space of all vector fields is merely a module. So that's a vector space over a commutative ring. And in order to fully explore the implications of that, in the next lecture then, I will talk briefly about modules and what you can expect of them and what not. All right, but first we have a very brief section, 4.4, cotangent spaces to a manifold. Cotangent spaces, and an important notion, the so-called gradient of a function. Now, having constructed last time the tangent spaces, it's actually quite simple to come up with the cotangent space. So let M be a smooth manifold suitably equipped with a topology and a smooth atlas, then the cotangent space and normally it's given the name TP star M, so you put the star there, that's the cotangent space, and well, this is more terminology. This is simply the vector space dual of the tangent space. The tangent space is a vector space, so this star makes sense to use, the vector space dual, with the thus inherited addition and S multiplication, and this is simply notation that you let the star jump here. It means, well, it means just this. Okay. So then the cotangent space is this vector space dual, and of course the cotangent space as the vector space dual is again a vector space. There is no secret here, and since we have a finite dimensional manifold, so remark, if the manifold is finite dimensional, and the way we defined manifolds, they are always finite dimensional because you always map into some RD. So we didn't include in our definition the possibility to have an infinite dimensional manifold. That can be seen as a defect. And in fact, if you want to do this, you have to go through some more trouble. Not much more trouble, but some more trouble. So I decided to only look at finite dimensional manifolds. And if or since the dimension of the manifold is less than infinity, it follows that the dimension of the vector space, tangent vector space, dimension is less than infinity, since they're the same, these two dimensions. We showed that last time, and hence it follows that the tangent space and the cotangent space as vector spaces, they are isomorphic as vector spaces. There is a word in order here. they are isomorphic, and being isomorphic as a vector space means there exists a bijective linear map between them. There exists a vector space isomorphism between them. Now you may ask which one. My answer is many, but none of them can be constructed without extra structure. So I can provide some extra structure, and then I can construct this isomorphism, and that then presents a proper isomorphism. So it's true, there exist isomorphisms, but we call them non-canonical because from the pure vector space or covector space structure, it cannot be constructed alone. This seems to be a very subtle point because you can say, well, usually if you provide a map, you always have to provide, say, the entries in the matrix that defines the linear map, right? I mean, it seems kind of natural. But the question is, can you provide this map without picking arbitrarily such a matrix? The answer is here, no, you can't, but nevertheless, it's isomorphic. It was quite a different thing with the vector space and the dual of the dual, and that's on the problem sheet you're currently working on, I guess. So the vector space isomorphic to the dual of the dual, and for that there is a canonical isomorphism. You don't need to provide extra structure in order to construct such an isomorphism. Anyway, so because this is often discussed, canonical and non-canonical, canonical means you don't need to provide extra structure beyond the level at which you're discussing this, and we're discussing this at the level of bare vector spaces. All right, fine. So you have this. So you see we had a nuts and bolts approach, if you want, to construct the tangent space at a point with the curves and then the directional derivative operator to the curve. We collected this. You see, we constructed everything really step by step. But for the cotangent space, that's simply not necessary because you just take the vector space dual. So what we did at this point is we look at our manifold M. We go smooth manifold M, or differentiable at least. We go to a point P, and at this point P, really only at the point P, we constructed the tangent space, and hence, quite trivially, the cotangent space. And obviously, I could now also construct the entire tensor space here, right? So, yeah, similarly, one can construct a space that we may call T, P, M. How did you call this before? We called this T, P, Q, V, right? So to stay in this notation, we should call this TRS of TPM. So TPM is just the underlying vector space, you see. And we could construct this as the set of all maps, okay, let's call them small t, too many capital T's around, small t that goes from R copies of TP star M, R copies taken together with the Cartesian product, and then you take of the tangent space without the star, so there's a star, you take S copies, and you look at the multilinear maps from here to the real numbers, and you can also require that they're smooth and so on. And not smooth, sorry. No, it's a pure vector space thing. Sorry, it's a multilinear map from this collection of vector spaces at the same point, here the cotangent space, and this would be the tensor. So this T is the tangent T, and this is the tensor T. They're different T's, all right? Okay, according to our previous notation that we take TRS of some given vector space, and if we take the tangent space as a foundation, and here we have the cotangent space, then we can construct all the tensors at this point, all the RS tensors at this point. We can construct this, comma, the set, and we know even vector space, because it can be equipped with pointwise with addition and S multiplication, even vector space of all RS tensors at P. Of course, if you have vector space, you have its dual, you can construct every every tensor. So really the only time we have to really construct this from scratch, this kind of object, is if you construct the tangent space with the curves and the tangents to the curve. And everything else, by mere linear algebra, so you have referred to the previous, second previous subsection, by pure linear algebra, everything else is generated. So tensors have nothing to do with differential geometry. Tensors have all to do with linear algebra and these multilinear maps. The only thing we had to construct was an underlying vector space over which then the tensor space is built, is constructed. But we're always at this point, at this one point P. All right, so now that we're speaking of the tangent space here, we have another important definition. Let f be a smooth function on our smooth manifold. Then at every point P in M, we have a linear map. We have a linear map, and this linear map has the name D. Now, if you want to emphasize that we're looking at this D only at one point, and we need to emphasize this at the moment, I write D sub P. So for every point, you have a different map. Okay, that's one thing. And what does the map do? Well, it acts on the, it acts on the smooth functions, and it takes you to the cotangent space at that point. That is why it depends on the point. Okay? You take a smooth map, which lives on the entire manifold, and you map it there. So how is this guy defined? Well, so a smooth function is mapped to d sub p of f, and this d sub p of f is supposed to be an element of the cotangent space. So how can I prescribe how that looks like? I need to say how it acts on an arbitrary vector. If I know that, I know what element it is. So it's defined by d sub pf. It's defined by its action on a vector x. And that vector x, of course, has to lie in the tangent space. Let me emphasize this. X lies in TPM, of course. And what else should this act? Okay? And the definition is particularly simple. It's simply the action of f of x of the vector field on the function f that was provided. Now this seems to take formalism to an extreme. You say, okay, you give me a function x, and then you define a map, dpf, that takes you from here to here, all right, but all you really do is, in the end, act with this on a vector, and you could have so much more simply written down xf. Why on earth do you write it in this complicated manner? Well, the answer, of course, is I want to look at this object here. It's very useful to look at this object without providing the vector it acts on. We don't, I mean, it's like normally in analysis you often want to talk about the function as such and not only the function f of x, the value of the function at some x. You want to talk about the function alone. And this is exactly the case here. So we have a linear map and called the gradient operator. So we have the linear map. So this guy here, this linear map, is called the gradient operator. And then dpf, a gradient operator at the point P in M. And then dpf is the gradient of the function f at the point P. Okay. And so we immediately observe that the gradient of a function is a covector, not a vector. Okay, it's a covector, not a vector. So in particular, you often hear the statement that the gradient stands orthogonal on the level lines of the function f. Right, you use this very often, that the gradient is orthogonal to the level lines. Well, but if you talk about orthogonal, you all know that what you need is an inner product in order to decide what orthogonal means, right? But let's assume I do not provide this inner product. I have a bare vector space. I have this bare construction without any inner product being in sight, which is the case here. I don't need an inner product because I can simply say, so that's remark A. Remark B is, let x be tangent to this. Okay, so let x be tangent to a level set. What's a level set? Well, n sub c of f. And that's all those points P in M where f of P equals C. So C is a real number. That's the level set. If I talk about x being tangent to the level set, I didn't define this formally. We'll come to that later more precisely. But the idea is I have in a, say, three-dimensional manifold, I have on there a function. It could be that this function is, say, constant on the surface of the sphere. Maybe there's a bigger sphere or something where it's again constant, but then it's clear what the tangent to the level set means. So this is now really the x in the big space in which this level set is hopefully at that point a smooth submanifold. So I can take the tangent. Well, if you have that, then it follows immediately that dpf of x, and that's a point P in the big manifold where you look at, this is automatically 0. It's because a covector acts on a vector and annihilates it. And it's a kind of perversion in standard vector analysis to actually take this covector, use the metric, if you have a metric, an inner product, to lift the index, to construct, use the metric to construct a non-canonical isomorphism, to lift up the index to make this a gradient vector, and then to again use the inverse metric, use the inverse metric to make it a gradient vector, and then use the metric again to dot this new gradient vector into another vector, because the inverse metric you use to make this a vector and the metric that you use to dot one into the other, of course, cancel each other out. Okay? It's totally perverse to do that, because the gradient naturally is a covector. Okay, so this statement, the gradient is orthogonal to the level sets, is a statement that doesn't need an inner product for the statement to be made. Okay, so but that's just an aside. What we can now do using the gradient, gradient is useful in itself, but it can in particular be used to construct a basis of the cotangent space. Gradient map or gradient operator can be used in the definition. Let P be a point of a smooth manifold, and let Ux be a chart that contains P. So P lies in the chart domain. Then, well, it's a definition and a theorem. Then we can take the dp, this gradient operator, and let it act on the illustrious function x1. And we remember that x was a homeo from u to x of u, which lies in Rd. But then we also remembered that last time talked about that then the components, so this is a part of Rd, so it has component functions a equals 1 to d from u to r. If this is homeo, this is continuous. Well, but it's even more than continuous, because for any map, for any such function, I can decide whether it's smooth. And with our definition of smoothness, this map was even smooth. You remember? The component functions were smooth. So I can act on, say, the first component functions with this gradient operator. And what do I get? I get an element. Let's look here. I act with the gradient operator. I get an element of Tp star m. Agree? And I can get another element of Tp star m by acting on the second gradient function, on the second chart map, component of the chart map. And I can do this for all the d, and d here is dim m, for all dim m component functions of the chart map, and I get dim m many covectors. Okay, the tangent space had dimension dim m, we already know that. Because we're finite dimensional, the cotangent space has the same dimension, because it's isomorphic. That means we have here a candidate, at least, for a basis, because we have enough of these covectors, and in fact it is a basis. So this is called the coordinate-induced or chart-induced covector basis at the point P. Now, this is definition, it's called a basis, but is it a basis? So this is one of these definitions theorems where you have to provide a proof, and rather than going through all the yakety-yak again, we can very simply apply this. So we take the eighth, so for any a equals 1 up to dim m, I take the eighth covector constructed this way at the point P, and because it's a covector, it can act on any vector. That's the job of a covector. It's a linear map that takes a vector to the real numbers, and I choose to act with it on these guys, the d by dxb's at the point P, and you remember those were the this is the bth member of the coordinate or chart-induced basis of the tangent space, which we constructed from the component maps last time, right? So I act with this on that, and let's see what we obtain. And from what we obtain, we'll immediately see, yes, it's both a generating system and it's linearly independent. So let's calculate this thing. It's also good practice to calculate this. So what's the abstract structure of this? How do we calculate this guy? It's a mere application of the definitions. So this guy here is just a smooth function. Then the dp can act on it. So, but how is it then defined? If this d of a smooth function acts on a vector, by definition of this d sub p, this is just the vector xb at the point P acting on the function that was provided. That was this definition. But now we have to see, what precisely was the definition of this beast? It looks deceivingly similar to what we usually call a partial derivative, but I cautioned you, this is not a partial derivative. This is this special object in differential geometry where you must refer to a particular coordinate system, unlike the partial derivative where no such thing is needed that you call the variables certain names. You rather say you derive with respect to the bth entry. Okay? And indeed, this guy acting on a function was defined as, so that's now the definition of precisely this guy, d by dx a sub p, that tells us this is the partial derivative in direction b, with respect to the bth slot, I should say, of which function? Well, now you need a function from r n or r dim d to r. It was this partial b, and then you took the function on which you act, that's this guy, you take the function on which you act, xa, and you compose it with, and now this x down here instructs you to take x inverse. This was the definition. So this x here, I mean this x is really this x because, okay, but because it's here, you have this x inverse here, you have this a there, and this b instructs you to take this partial derivative there, and you do all this at the point p, and you have to evaluate this whole guy at the point x of p. Right? So this was this definition. Now, we also saw that this guy here is simply the projection map to the eighth component, and that's a map that takes you from r dim m in this case to the real numbers, namely you take the eighth entry of this dim m tuple, means dim m times Cartesian product of real numbers, and you produce the eighth entry. But it's very simple to see that this is 0 whenever b is not a, because this projection map maps you straight to 0, so the derivative is 0. And if b is a, the projection map brings you in the eighth component, it's the identity, and then yes, and then the derivative is a delta a b. It doesn't matter where you evaluate it, it's everywhere, either 0 or 1. Aha, so what does this show? So if you start reading here, we have a covector, we have a covector, we have dim m many covectors, dpxa. They can act on a basis, that's the point. If you let b run from, so a and b run over this range, you plug in one basis element after the other, and you see for every basis element here, you find one here that does not annihilate it, and all the others annihilate it. So that shows that these must have been linearly independent, otherwise that wouldn't work. And they're also enough, so it's also a generating system, so it's a basis. But we have, from this proof, we actually proved more than we wanted to prove. We even proved that dx1 to dx dim m, and if you insist, we can emphasize we're at the point p only, thus this is not only a basis of the dual space, is even the dual basis, is even the dual basis of the dual of the dual of TPM. And we all know that the dual of TPM I could call, or we did call TP star M. I chose this more arcane formulation here because I wanted once more use the word dual twice in the same sentence to show that they have slightly different meaning here. Here the dual of TPM refers to this star, and here the dual refers to the application of one basis to the other, resulting in a delta AB. Okay? So these guys really provide the dual, the chart-induced dual basis to the chart-induced basis. Okay? This is all very simple. It's just important to not look at this dx1 the way we so often do in undergraduate physics. We say it's a small change in x1 or something like this. I mean, this, what is this? It's precisely this map up there. And that makes full sense. And then once you have this, you have full technical control over what you're doing here. Hence, it's important to dissect this kind of sometimes a little bit to the uninitiated, maybe sometimes a little bit mysterious notation. Everything is very precisely defined what it means. and it means nothing else. So whenever in the future you meet a dx1 to dx dim m or something, for instance, in the measure of integrals, you meet this, not dx1, dx2, dx3, multiple integrals and so on. And we'll come to this. Actually, there's a wedge product between that. We'll come to that. But this is exactly what appears under the integral. And it's not just a symbol. It can be dissected in this way. It's very important that you do so if you want to do analysis on a smooth manifold. The next short section is a very important one. There are two important concepts being introduced, and that's the concept of a push-forward map, push-forward for short, push-forward and its cousin pull-back. What is this? So definition. Let phi be a smooth map between smooth manifolds. We know what that is. Now you have to choose, you have to look at the atlas for M. There is an entirely different atlas in general for N, right? So we said when I say M and N are smooth manifolds, then you think this has a topology in atlas, this has a topology in atlas. And of course, at first they're unrelated, or they're unrelated in general. And then via pushing the phi down to the charts, right, to the chart representation, you define when the phi is smooth. Right? We did this several times. So that's what we're talking here. Let this be a smooth map between smooth manifolds. Then the push forward, and it has a name that's phi up star. It's another star. It's nothing to do with the dual star. Then the push forward phi up star of the map phi at the point P in M, so that's the full family name of the guy. Then the push forward phi up star of the map phi at P in M is the, again, linear map, is the linear map. Well, again, the name is phi up star. From where to where does it map? It takes an element of the tangent space to the domain, TPM, at this point P, and it takes you to the tangent space in the target at the point phi of P. So it's not the same point P. How could it be? Because P lies in the domain. If N is a different manifold, well, I can use the map phi to map the point P in M to a point in N. I mean, that's the only point that's distinguished in N if I give you a point in M and you have a map from M to N, right? It's the only point you can distinguish. And it's really between this tangent space and that tangent space. So if the phi is between the manifolds, you pick a point, and then the push forward takes you from the tangent space at this given point to the cotangent space at the image of that given point. Okay? And how is it defined? It's defined, well, you need to take an element x of the cotangent of the tangent space here, and you map it, not surprisingly, to phi star of x. But you've got to see how this is defined. Defined by, so we have to say what phi up star of x, what this actually is. Now, how do you say that? Well, it's supposedly a vector in an element of the tangent space of the target. Well, if it's a vector, it can act on a function. And if I know how it acts on an arbitrary function, remember vectors are directional derivative operators, if I know how it acts on an arbitrary function, I know what vector it is. Right? That was the definition of a vector, but it's now a vector to this target manifold N. So I need to let it act in order to define it on an f, but this f is not a function on n, it's a function on m. Sorry, it's not a function on m, it's a function on n. Okay, it's a smooth function. Because this guy is supposed to lie here, in this tangent space. Okay, so clearly I need to prescribe this. There's no alternative if I want to define the result here to decide how I want to define this. But now the question is, how much choice do you have? So remember, the x here, this is an element from in TPM. This whole guy is supposed to be an element of T phi of Pn, and you act on a function on n. What choices do you have to provide a linear map? That's the key thing here, to provide a linear map. Well, you take the vector x and you act on f after phi. So with the data you have to do this, because what is f after phi? Well, phi starts in m, takes you to n, all right? And then f, being a function on n, as it must be if this is a vector on t phi p of n, takes you to the real numbers. Aha, that means f after phi is a map from m to r. And it's smooth, because phi is smooth, f is smooth, so this guy is smooth, a smooth map from m to r. Aha, so that means this whole thing here is an element of C infinity m. And the vector x, quite conveniently, is a tangent vector to the manifold M. And of course, it can act on such a function. Okay, so you do not need to remember this definition. All you need to remember is the push forward takes you from the tangent space of the domain to a tangent space in the target. Then it's clear this is P, then this must be phi of P, what other point is distinguished. And then by the mere requirement that this be a linear map, this definition is forced upon us. Okay? So don't memorize stuff you don't need to memorize. So I every time construct this when I need it. It's pretty obvious that this is this thing. Okay, so that's the push forward map. Now remark, I just said it, A, this is the only linear map that can be constructed from these data, can be constructed, well, it's the only such linear map, meaning mapping from TPM to T phi of PM. This is the only linear map, such linear map that can be constructed from the given data. That's the first remark. And the second remark is that phi star, and if you want to be very precise in the notation, you may also put a small p down here to recall that this map is defined. There's a different such map for every p. Okay? At every point we have this. Then phi up star p. No, it's not up star. I'm sorry. It's a. Oh, I'm sorry. You see, I always. The push forward is usually labeled by down star. Okay. So how is down star? Obviously, this has no real significance, but it's the standard convention, and we would like to stick to the standard convention. So the push forward has this down star, and phi down star p is often called often called the derivative of the function f at the point P. So if somebody talks about the derivative of a smooth function on a smooth manifold, what people mean is this induced map. It takes you from the tangent space to the tangent space. Okay, that's the derivative. So the derivative is synonymous with the push forward. And push forward is a very good name because it pushes vectors from this tangent space in the domain to that tangent space in the target. It pushes them forward, meaning in the same direction in which the map goes. So the map went from M to N. Well, if it's a bijective map, or even if diffeomorphism, bijective and smooth in both directions, then of course you could also have immediately a map from N to M, namely the inverse. But very often maps are not invertible, but they can nevertheless be smooth in one direction. And then the statement is, even if the map is not, so particularly if the map is not invertible, you can still push every vector here in the domain to a vector in the target, right? In the same direction, and that's why it's called push forward. Forward being defined by the direction of the original map between the manifolds. That's the terminology here. And I guess there is another comment in order, just remember. So how was that? Well, it's more like a, yeah, let's keep it a remark. The tangent vector x sub gamma comma p of a smooth curve is pushed forward, probably without a hyphen, is pushed forward to the tangent vector of the smooth curve at the point P, yeah, is pushed forward to the tangent vector of the smooth curve, let's say gamma, of the smooth curve gamma at P is pushed forward to the tangent vector of the smooth curve phi after gamma at the point phi of P. Okay, so illustration. The manifold M, it's the manifold N, and in M you have a curve. This one is the curve gamma, and let's say this here is the point P, and then you have a tangent vector, and now you see I do something terrible, I draw a little arrow, but you know this is just our illustration for the derivative operator, the directional derivative operator that such a tangent vector is. But because you already saw that in charts and so on, this after all corresponds to a dim M tuple of numbers, namely the components with respect to this and that basis, I allow myself to draw this arrow just for illustration purposes. But you know it's actually this operator. Right? We have, so, and now, and that's the key thing, there is this map from the manifold M to the manifold N that I provide. What does the map do? It takes this point to that point, and takes this point to that point. So it takes every individual point to that point, but in a smooth manner. Okay, it maps all the points. Well, because it maps all the points, in particular, it maps the points where the curve lies. And so you can look at the image curve. Let's have that yellow or something. The image curve can now look like this, and well, maybe it should be double colored because it's made up of phi and gamma. This is the curve phi after gamma. Right? It's the image of that curve, and as much as every point is mapped, the point P itself is mapped to the point phi of P. This map in particular takes this point to that point. Of course, that's part of the curve. And you can ask, what is the tangent vector here to that curve? Because once you mapped the curve and once you mapped the point, you don't need to push forward. You can directly construct the tangent vector because you have a curve, a smooth curve in a manifold, so you can construct the tangent vector. Now, the claim, however, is that if this is the tangent vector x, the green one, then this tangent vector y here, which lives in the tangent space to this different manifold, then this y is nothing but the phi push forward of the x. That's the claim. You get this tangent vector over there. Or if you want to use our notation so formally, so that's the idea. So how do you do this formally? You claim that the push forward of the tangent vector x gamma comma p is the tangent vector to the curve phi after gamma at the point phi of p. That's the claim. Okay? Proof. I mean, the proof is very simple, but it's good practice for this formalism. Okay, well, let's just start on the left-hand side and see where this takes us. Phi star at the point P, okay, we can overdo it, gamma comma P equals. So how is the phi star defined? It's here. We actually only fully understand this, or we can only work with it properly if we let it act on an arbitrary f. So let f be an arbitrary smooth function on the, no, not on the manifold M, on the manifold N, on the target, because this is supposed to be a vector in the target, right? Let's let it act on some f, and let's see whether we come from here to there. Okay, so how is this defined? Well, here's the definition of the push forward. What does it tell us? It tells us take the vector that's it acts on, take this vector, and then act on, there we said it, f after the smooth function phi. That's the definition of the push forward. Okay. Well, we're obviously not here because this is x gamma p, not x phi after gamma phi of p. So how do we continue? Well, now we use the definition of the tangent vector. Very simple. So definition of the tangent vector to a curve. So it was the first definition last time, I guess. What is that? Well, you take the function f after phi after the curve that's mentioned down here. You remember? So this was before always the function, so we take this function, you do this, and then you take the derivative at 0 if you provide it for the curve to go through the point P at 0. So for this proof, arrange for gamma of 0 to be p. If gamma of some other value is p, you put this other value here, right? I mean, arranging for, it's, yeah, fine. So you have this guy. And now it's obvious, it's this guy, that's right. So, and now we had the brackets like this, that's where we came from, but the composition is associative, so we can put brackets like that. And then you stare at that for a moment, and then you see, this is again, by the definition of the tangent vector, now you use the definition backwards, it's the tangent to the curve phi after gamma, namely this curve here, phi after gamma is also a curve, as it acts on the function f, right? This is now a curve in n, and this f is a function in n, all right? And all of this happens at the point phi of gamma of 0. But that's phi of p. So this is the tangent vector to that curve at the point phi of p as it acts on f. All right? That finishes the proof because we can box this operator, and we box this operator, and on an arbitrary function they do the same. That means as operators they are the same, and that is the claim. So it's just plugging in the definition twice, and you see this. Okay? So that's the geometric notion and intuition of the push-forward map, or, as it's called, the derivative of the function at that particular chosen point. But you can do this at any point. Now there's the cousin of the push-forward. That's the pull-back definition. So again, let phi be, as before, a smooth map from M to N. Then the pullback, and now the pullback has the star up. Okay, then the pullback phi star up of the map phi. Now, well, at the point phi of p in n, so the pullback refers to a point in the target, and yeah, phi p in n. Hang on, do I need to do it like that? It's a phi of a p. It must be the image of 1. Yeah, I think I need to do it like this. At phi p in n is the linear map. It's the linear map phi up star. And now I write it down in an unusual way. It goes from T star P, so it's the same business as before, that you can actually label this with the point you're talking about here. It goes from T star PM to T star phi of P N. So it looks like before, only that instead of going from the tangent space to the tangent space, we go from the cotangent space to the cotangent space. But the big issue here is that the arrow is in the opposite direction. Okay? And it's in the opposite direction to this arrow, and that is why it's called the pullback. If you look at the cotangent spaces, you go in the opposite direction from the original map. Again, if this map is a diffeomorphism, you can go back and forth. Well, you can immediately write down the pullback of the inverse, which then goes in the same direction. But that's not always the case. Sometimes this is not, say, surjective. If this map if this manifold has a higher dimension than this one, it can't be surjective. Then it can't be inverted. Okay, and of course, normally people take this thing, put it here, and take this cotangent space and put it there, and keep the direction of the arrow according to the standard notation. But for dramatic effect, I put it here like this. Is this linear map? And actually, I could now set it as a homework problem, but it's too important to not do it right now. How can we construct this map? Well, let's try to do this together, okay? So what do you have to do? You have to take an element here, okay? So you have to take an element in the cotangent space in the target, and let's call this element omega. It's a covector, right? A covector in this manifold. And you map this covector to what? Well, obviously to phi star of omega at the point P. Well, that's nothing new. But the statement is that this is a linear map. This is a linear map. How can we construct this guy? Okay, defined by. So let's do this together. This is supposed to be an object in TP star M. So how can we define what a covector is? What do I have to do? You tell me. Let it act on a vector in TPM. Right. Okay. Defined by, take phi up star of omega and let it act on an x, but this x ought to be an element of TPM. And we need to define this. Okay. Now the result will of course be a real number if we're at the point P, so you can immediately start defining this. But it's not just any map acting on a vector, but it's a linear map acting on a vector. So whatever you write down now should be linear in this entry. Are linear in this entry. Okay, the only thing you're given is the map phi and the vector x and the covector omega. Omega lying in the cotangent space of an entirely different manifold, namely the target. Okay. What can you do? Suggestions? Yeah? Let the push forward of x, very good. So we want to define the pullback, but we use the push forward. We decide at which point in a second, and let it act on the x. So x is an element in the tangent space of M, so it needs to be the push forward at the point P. Okay? Does this work? Well, yes, because phi takes you from M to N, so the push forward takes you from the tangent space TPM to this tangent space. Where are we? We're now in the tangent space T phi of P N. That's right, no? That's where it took us, the push forward. But we haven't used the omega yet, and this is not a real number yet. So what do we do with this? You said we let this act on omega, right? Okay, exactly. Why is this legal? Well, because the omega is an element, by assumption, of T phi of P star N. Oh, fantastic. So really this... it's the other way around. You have to let the omega act on this. Okay, yeah. No, it's fine. You could define this action too, but it's clearer if you let the omega act on this. It remains true. The omega is an element of T phi of P N star. So it can act on this vector and it produces a real number. Now the question is this linear? Well, it is, because the push forward is linear. We didn't check this. You might want to check that. This is linear, and the omega is linear again, so everything pulls out. Sums pull out, and factors pull out to the front. Okay, so the whole thing is really linear. And again, that's why I had it construct U here. It's the only way you can define this thing. So again, of the push-pull back, you only need to know from where to where it maps, and most important, or as importantly, that it's a linear map. Then the then the pullback is fully defined. That's it. That's the pullback. Now, there is a, there's a motto, I don't know, memorize the following. Memorize. Vectors are pushed forward forms, or covector forms is an extension, we'll come to that later. Covectors are pulled back. And only under special circumstances, namely if the map phi from the manifold to the manifold is a diffeomorphism, you can go back and forth, then of course you can also pull back vectors, but then you use the inverse map phi. But if that inverse doesn't exist, generically vectors can only push forward and covectors can only be pulled back. It's a very important idea. Okay, so come back to that in a second once we define what immersions and embeddings are. Okay, so we can now use the push forward for the following application. Decide the question under which circumstances some manifold, some smooth manifold, can sit inside an Rn, can sit, in quotation marks, in some R to the n. Okay, so why do I use this non-technical term sit? Well, because there are actually two notions of how a manifold can sit in another one. In particular, I choose Rn because that's immediately intuitive. You can generalize this to one manifold M sits in another manifold N, but this N is here R to the N. And there are two notions. One is that of an immersion, and the other one is that of an embedding. They're slightly different notions of sitting. One manifold sitting inside another. Two different notions. There is immersion and there is embedding. And embedding is the stronger one. So every embedding is an immersion, but an immersion is a slightly weaker notion, has less conditions than an embedding. And it's useful to look at both. Sometimes you're happy with an immersion, sometimes you want to have an embedding. Okay, so definition. A smooth map phi that takes the manifold M and sends it to a manifold N, but, well, I said here for illustration purposes, I wanted to look at the specific smooth manifold R to the N. A smooth map phi from M to the R to the N is called an immersion of M into Rn if, only one condition, if the derivative of f, what was the derivative of f? Was to push forward, right? So derivative of f immediately translate to push forward. If the derivative of f, phi, of course, I'm sorry, of phi. So what was that? Push forward was down star. If phi down star, you have to pick a point. Okay, goes from TPM to T phi of p r to the n. If the derivative of phi, namely this push forward, which is a linear map, is injective, where? At which point? Well, at any point. At any p in M. That's it. It needs to be injective. Injective means the same target vector is not hit twice. They're not two different vectors to the original manifold that map to the same target vector under the push forward. That's injective. You know that. Okay. If that is the case, you have an immersion example. Well, you have to check this technically, but I leave this as a homework. But you could look at the manifold M being the circle, and you could look at n equals 2. And I can provide different maps. So I could provide example A, the map phi from S1 to R2, that does the following, that takes the circle, but this is just supposed to be the points of the circle, It maps every point of the circle into R2, so into this space, and does so in this fashion. Well, that's smooth because you didn't produce edges, so you didn't produce something like this. This wouldn't be a smooth map, right? This is a smooth map. It takes you there, and I tell you it is injective. No two vectors, tangent vectors here, are mapped to the same tangent vector over there. Well, again, you should actually calculate this, but intuitively, at this point of the circle, you know the tangent space is one-dimensional. Well, if I already think of it in an embedded way, then you have vectors that show in this direction, tangent vectors that show in that direction. Those are the only tangent vectors. And they're, of course, mapped here by push forward to these guys, and they never coincide if they didn't coincide in the original manifold. It's very simple. Okay, so this is an immersion, namely of the circle into RD. You could, of course, also take the circle and immerse it into R3. That would then look like a loop here in space. So it's fine, as long as it gets no corners. Well, a second example is the map phi twiddle. It's another map. Also takes S1 to R2. But now in the following fashion, all the points of the circle are taken in R2 to this guy. Okay. So the first question is this map phi twiddle, is it smooth? Yes, it is smooth. You can check that this map, I mean, write it down. You use some sign and in this direction and some sign in that direction with a double frequency. You know, it's like Lissajous figure or something like that, okay? You can construct this. And you can check that this map that takes you from there to there is smooth. It's a smooth map, okay, fine. Now the question is any vector, tangent vector here, any two tangent vectors here taken to the same tangent vector there? No, they're not. You might worry. I mean, the immediate worry is about this intersection point here. But there is no worry, because at this point here, so this point may go to that point, right? But it may go to that point in the sense like lying on this branch if you move past here. And then you might also look at, say, this point here that's mapped to the same point but belonging to that branch, okay? And this is an issue of the map phi twiddle. That's the map phi twiddle is not injective. Clearly not in this case. Phi twiddle is not injective. But that doesn't mean that its derivative is not injective. And of course it is injective, because you see this vector and that vector, they always go to this vector and that vector. And the vectors here, they're different here. But of course the resulting tangent vectors are also different there. They don't coincide with the others. So here, phi twiddle, not injective. But so what? That was not required. But again, phi twiddle down star, so the derivative or the push forward is injective. Proof, well, formally, but you can look at the picture. So again, phi twiddle is an immersion of the circle into R2. Aha. So you see, an immersion is not such a strong condition. Well, there is some conditions. It's injectivity, but it's not that strong. So the stronger notion is the notion of an embedding. Define a map phi from M to N being smooth is an embedding if A, phi is an immersion, so it shouldn't be too difficult to show that embedding implies immersion, because it's one of the conditions. Phi is an immersion. And B is that if you map the entire domain, the first manifold M, okay, now I wrote N, okay, you can substitute. If I take the entire phi, if I map this by the smooth map, then I should be homeomorphic, so I should be topologically isomorphic to the target manifold. Well, why only topologically? Well, if it's topologically and phi is smooth, but it's one-to-one, then it immediately implies, but you don't need to request this, it immediately implies that it's also diffeomorphic to n, but you only need to check whether the image is then again a manifold, and that is if the image is a submanifold of the target. Now, this extra condition says that the example A from before is an embedding. This example A from before, the circle goes to this funny distorted circle. This is an embedding, so I write down again, the circle goes to this thing is an embedding because this is again a manifold. It will also be a smooth manifold because phi is smooth, so everything you produce. And that's the idea of an embedding. You can think of the smooth manifold as an immersed submanifold of the bigger space. Right? That's fine. Whereas the example B from before, which was an immersion, is not an embedding. Not an embedding. And if you look at it again, of course not. Well, because what would possibly be the dimension of this manifold at this point here? At this point, it's not locally homeomorphic to R to the 1. It fails to be a manifold. Okay? So, and sometimes you insist on this being a manifold, and okay. So now that clarifies the notions, the two notions one usually looks at of what it means to sit, one manifold to sit in another manifold. But what's the answer to the original question? Under which circumstances can you have a given manifold sit in some R to the n for a suitable n? And that is clarified by the Whitney embedding and immersion theorem. So we quote the theorem by Whitney, and that's the following. Any smooth manifold, M. Oh, that's good news, because I asked under which circumstances. It could be that there are smooth manifolds that cannot be immersed or embedded, but the theorem starts in a promising way, and it stays promising. Any smooth manifold M can be, first, embedded in R to the 2 dim M. Full stop, well, comma. And it can be, okay, before I come to when it can be immersed or where it can be immersed, so any smooth manifold can be embedded. The only thing is that the embedding space R to the n must have up to, in the worst case, it must have up to double the dimension of your manifold. Okay. There are some smooth manifolds that can be embedded in an R2 dim m minus 3 or something. Yeah, well, yeah, that's true. But it depends on the dimension, it depends on the manifold. But the worst case, I think the worst case provided by projective spaces on, you need to double the dimension. Okay. So the circle is one-dimensional, and the Whitney theorem tells you, well, because the circle is a smooth manifold, it can be embedded in R to the 2 times 1. Ah yeah, the circle can always be embedded in R2. Well, that's not a big surprise. We already gave an example, but of course the Whitney theorem is true for any smooth manifold. So any one-dimensional manifold can be embedded in R2. Any. Okay, any two-dimensional manifold, the sphere, the torus, tralala, can be embedded in R4. Do you know of a two-dimensional manifold, we already had it on the blackboard, that cannot be embedded in R3? So, I mean, we should find a counterexample that a two-dimensional smooth manifold can be embedded in R3, that it needs to be at least R4. The Klein bottle, that's right. The Klein bottle can't be embedded, but it can be immersed. Well, indeed, the immersion is a weaker condition, and the embedding theorem takes account of that by stating that it can always be embedded in 2 times dim m minus 1. In 2 dim m minus 1 dimensional Euclidean space. We call R to the n, we call this Euclidean space, if we consider it a smooth manifold and so on. So there you can actually go 1 dimension down. So, well, the example, if you wish, is the Klein bottle. So now I try to draw the Klein bottle. I tried this several times. Let's see whether this time. So there's this part of this kind of throat here. So now comes here this, okay, let's say like that. Now, at one point we come out here, and this is just this part here. So there you kind of go in, and it looks somehow like this. So it's like you take a torus, and then you don't go together like this, but you go in somewhere else and join it from the other side. So this is the Klein bottle, and you see it intersects here. And so this intersection is obviously a two-dimensional manifold in R3, because this is supposed to be a picture in R3. And you see here it intersects itself. That's really very much like here, this intersection, like the intersection we had before. I draw it again here, in this case. Okay, and this prevents it from being an embedding, because this image, so you have the Klein bottle K is mapped to here by phi, but you see phi of K is not a topological manifold, right? In particular, if it's not a topological manifold, it cannot be topologically equivalent to this K, right? So, but this is an immersion, not an embedding. So, two-dimensional Klein bottle can be immersed into R to the 2 times 2 minus 1. That's, of course, R3. Well, that's what we did. So, perspective picture in R3 can be immersed, but not embedded, since for embedding worst case of Whitney theorem for the Klein bottle. And indeed, Whitney would guarantee it can be immersed in 3-dimensional, but it cannot be embedded. It guarantees it can be embedded in R4. And the Klein bottle is an example where you can't beat that limit. For some other manifolds, you can obviously beat that limit. Okay, like for the sphere can be immersed into R4 for sure. I mean, the 2 sphere, but it can also be immersed into R3. Okay. Now let me think for a second. M2. Yeah. Okay. That's the Whitney embedding theorem. And actually there is a slightly stronger version. So this is already called the strong Whitney theorem. And that takes some effort to prove. You can prove weaker versions. A weaker version you can prove is that you can embed into some Rn. I mean, also that is not obvious from the beginning, that any manifold can be embedded in some R to the n. Okay? That can be proven more quickly. But anyway, there is a stronger version. So there are even stronger versions. There are versions. And one of them is the following: any smooth, so e.g., because under certain circumstances you can make this bound better of the dimension. Any smooth manifold can be immersed. So that's one. It talks about an improved bound on the dimension here. Can be immersed into into R to the 2 dim m minus A of dim m. And the question is, what is A? Where A of some integer number n, non-zero integer number n, say, is the number of ones, so this is the number of ones, in a binary expansion of M. What does that mean? Well, example, let's say you have a manifold of dimension 3. Then this is the 3 is in the decimal system. But you can expand this as 1, 1 in the binary system. Because this is 2 to the 1 plus 2, 1 times 2 to the 1 plus 1 times 2 to the 0. Right? It's the binary number 3. And so therefore, A of 3 is 2, because in the binary expansion you have 2 ones. So therefore, the stronger theorem says any three-dimensional manifold, any 3-dim manifold can be immersed into R to the 2 times 3 minus 2. And that's only R, 6 minus 2 is R4. Whereas even the strong Whitney theorem said it can be embedded in R 2 times 3 is 6 into R5. But you can be better because in dimension 3, the 3 is in binary expansion, it's like this. You can embed every three-dimensional, you can immerse any three-dimensional smooth manifold into R4. I find this quite amusing that there's the okay. I mean, if you need, in a particular case you're working with, you need an even better estimate, go to the literature. There are other stronger limits in certain cases. Okay, so there are further better upper bounds on the dimension of the target manifold on n in R to the n. Go to the literature, but they usually refer to particular additional circumstances, which, however, for the case at hand may apply or may not apply. But this is already pretty good, the Whitney embedding theorem. And again, I emphasize again, it clarifies this question of whether the intrinsic approach is more powerful than the extrinsic embedding approach and so on. the Whitney theorem says, no, it's not. It's really the same. You could construct, well, we didn't prove this, but you could now check whether the tangent spaces we constructed intrinsically are vector space isomorphic to the tangent spaces you would construct as tangent planes or higher dimensional planes to the embedded manifold, and you would find, yes, it's the same thing, okay? But there you need an embedding, because if you have only an immersion, you wouldn't know how to attach the tangent manifold, but then you go one dimension higher in the worst case, and you get an embedding of the same thing. So really the intrinsic approach, the extrinsic approach, and in the history are the same, and in the history of differential geometry, this was argued for some while, which approach is the right one, or are they equivalent? It turns out they are equivalent. But then the intrinsic approach is just more aesthetic. And it also, of course, then justifies that we draw the tangent space. If we think of a manifold, that we draw these tangent spaces like we intuitively draw them, this is ultimately justified by ideas like this. Okay, so now we come to yet another technically highly important topic, and that's the so-called tangent bundle. And associated with the tangent bundle, we look at vector fields. So far, we looked at a manifold, say such a manifold M. We looked at a particular point, and we studied the tangent vector, the tangent space at this point. Now I feel, after the Whitney embedding theorem, I feel more justified in drawing such childish pictures here. Okay, so we looked at the tangent space at one particular point. And that's the construction we look at. But now, consider the following definition. Let M be a smooth manifold. Then the tangent bundle is the set. So you see, we first bundle, you might already have the association of the of our manifold bundles, but we start slowly, is the set Tm. So you see there is this omission of the point P I'm talking about normally. This is Tm, and it's the union, and I emphasize it's the disjoint union of all the TPMs we looked at before if I take any point P in M. So I take, as a set, I take every individual tangent space. So I take this one up here, and I take this other one at the point Q. That's this tangent space, TQM. Now, it looks like these tangent spaces are intersecting here, but of course you're no longer fooled by anything like this, because that's an artifact of our embedding. Okay? If I had embedded this slightly differently here in a higher dimension, then they wouldn't hit. Okay? And we know intrinsically there is no such notion as these tangent spaces have any intersection. Right? They're just entirely different spaces, and that is what this dot here is supposed to emphasize. I mean, the dot never does anything. It just is an emphasis, because if the spaces are disjoint, they're disjoint. If they're not disjoint, you can put a dot here. They will still remain non-disjoint. So this is just the emphasis. These are considered, and in fact they are, disjoint spaces. They have no intersection. No element in TQM is an element of TPM. Okay? And now, as a set, you take all the tangent vectors at all the points of the manifold, and this set, this huge collection of tangent vectors at various points, you call Tm, the tangent bundle as a set. And further, we define the bundle projection map, or bundle projection. So you see we are moving towards the bundle. that takes us from this huge collection. So I have a whole bag full of tangent vectors, okay, come from different tangent spaces. But now you pick one of the tangent vectors from your bag, from your bundle, and you go and look. You say, okay, I have here, how do you call this element? I don't know, call it theta, psi, okay? Let's say psi is such an element of this tangent, but no, let's call it capital X, because you see, an element of the tangent bundle must be an element of some TPM, okay? And it maps the X to the point P. Now you say, well, what is the point P? Where P is the point, for which X, the X that's given here, is an element of TPM. Right? So you take some tangent vector to some point, and pi maps it to the point P that is the base point, as we sometimes call it, of the tangent space from which X comes. Now, can you identify the grammatical element in this statement that corresponds to this disjoint union sign? Which symbol here do I have to write in orange? Well, it's the V. Because there could be several points from where this X comes. No, it can't, because they're all disjoint. So the fact that you have an actual map here, that pi is a map, has to do with this being disjoint. So all of this is fine. So what we have now, we have a set Tm, we have a map Tm down to M. This already looks like a bundle, but at this point it's only a bundle of sets, a set bundle. It's not even a topological space bundle, let alone it's a smooth manifold bundle or a topological manifold bundle. It's just a bundle at the level of sets. Okay? So, so far, Tm pi m is a set bundle. By the way, at this point, I should clarify that in one of the previous lectures, I was asked to give an example of a non-fiber bundle, where not every fiber is the other fiber. And I came up a little quickly with the example where I have a manifold and I attach at every point a complex line, and all of a sudden I attach only real lines. Well, this is clearly a bundle. If I have this projection map on top, it's a bundle of sets. Okay? Because in a bundle of sets, I have no additional requirement for this pi. You see, I can't talk about continuity unless I have a topology here and a topology there. So my example was right. So there's this bundle of sets that's not a fiber bundle, because not every pi, so this is a P and this is a Q, and pi inverse of P, which we call the fiber at P, is simply as a set. As a set, it's not pi inverse of Q. It's not bijective, not isomorphic as a set. There's no bijection between, between this P and this Q. There's no bijection between R and C, right? Well, that's tricky, because there are these proofs that you can. Well, certainly you can get some fibers here and some fibers there, so that it's not a fiber. Okay, so you see, get deeper and deeper into trouble. But the emphasis I wanted to place was on the fact that actually the way I defined bundles in the previous lectures as bundles of topological manifolds, you need to have continuity here. But the biggest problem is that this total space, E, the M with these attached, is not a manifold, because if M is one-dimensional, say, then at this point the bundle would be two-dimensional, real two-dimensional, and at this point it would be real three-dimensional, right? So that's not, this is not a manifold. So this example is an example of bundles of sets, but it's not a manifold bundle, okay? So that was my sin there. I wanted to emphasize at this point that you don't take this example too seriously. In fact, it's really tricky to construct a non-fiber bundle for manifolds, but I think it's possible. Okay, anyway, so that was just an aside on some confusing statement of mine, although as a bundle of sets it can be held up, but that was not the context in which I presented it. Okay, so now, but here we have a bundle of sets. Now the question is, how do we make this into a bundle of topological manifolds, or even a bundle of smooth manifolds? Well, the M here is smooth, or I can require this to be smooth. Now the simplest would be if I was able to take a smooth atlas on M, which I'm provided if M is smooth, and to construct from it a smooth atlas on the tangent bundle. If I construct a smooth atlas here, I have a manifold, right? Okay. And now you could ask, oh, how do you define a topology here? So how would you do that? How would you define a topology on Tm? What do you want this topology to achieve? You want to achieve that pi would be continuous, right? So what do we know about? We have a topological space here. We want a particular map to be continuous. So which topology do you have to establish here? Last problem class. It's the initial topology. So I think it was on the last problem sheet, the initial topology. And then you could get a topology here, but now we want to immediately pull the entire smooth atlas. So want to make Tm into a smooth manifold. Idea: construct a smooth atlas on Tm from a given smooth atlas on M. Aha. So how do we do this? Okay, the picture is dangerous, but maybe it's quite useful. You have the manifold M, and at every point you attach the tangent space. This looks funny because the tangent space should be tangent, but now because I do not need to subscribe to the embedded notion, I can make a nice picture of the tangent bundle by putting them up here like this. And okay, so and this whole thing here is then Tm. So that's the picture we have in mind. But now let's see how we translate this into mathematics. So given from a smooth atlas on M. So more precisely, let curly A M be a smooth atlas on M. Then I can take some Ux from the smooth atlas. So some domain U and some chart map X. And for instance, I could take this U. There's an open set in M, and with this U comes some chart map into R dim M. Okay, we take this. And now I would like, from this chart on M, I would like to construct a chart on Tm. And the idea is to look, so construct a chart pi inverse of u. What's pi inverse of u? Well, pi inverse of u in the picture is this guy. Is that right? So you take the set u in M and you take the pre-image. Okay, pi inverse. Okay. So I always wrote well, let's stick to pre-image. It's the better notion. It's the pre-image of u under pi. It's usually denoted pi inverse, but that always has this taste of pi is invertible, which of course it is not at all. So you take the pre-image of u under pi, and that's of course this entire, well, set here in the intuition. Okay, well, that's a perfectly nice open subset of Tm if on Tm you establish, for instance, the initial topology. Let's say that has already been done. So now you construct this, and this is the new chart domain, but not now the domain on the base manifold, but this is now supposed to be the chart domain on Tm. And now you, instead of the x that you had before, the x gave every point here on of this u a coordinate. Now we need to produce a coordinate for any point in this pre-image of u under pi, if this is supposed to be a chart of Tm. You're all following, right? The idea is clear? Okay. And so this new chart map we call xi, and we construct it. So what is xi supposed to be? Where xi takes you from the pre-image of u under pi to some, well, to some xi of the pre-image of u under pi. And that is certainly going to be a subset of R 2 dim M. Why is that? Well, I mean, it's intuitively clear. It must be that because the tangent space has the same dimension as M, and in a sense, locally, if it's locally trivial, if it's, then it must be double the dimensions. It's totally clear. Okay. So, but we want to construct. I mean, this is just a claim. But now let's construct this map xi. Now, how do we do this? So we have to take a point in this orange domain, which is in the manifold, in the tangent bundle. So we have to take some point. Now, we shouldn't call it P. We call it, what do we call it? Well, we should call it X again, capital X. Okay, because it's the element of some tangent space. So we take this big X, which lies in the bundle somewhere, and we map this to, because that's what we're supposed to have, we're supposed to give this coordinates, and the idea is, and we have to show that this is then a fine chart map, we map this to the coordinates we had before of these points. But so the first idea is I take this x and I project it down to an element of this original u we had. How do I do this? Well, this point down here is pi of x. Do you agree? This is pi of x. So we take pi of x, but pi of x lies in the original u. So maybe we should, well, okay, my color coding might not be useful anymore, but let's do it like this. So this guy here is now a point in the original u, right? But as such, I can use the original chart map, and in particular the first component of this chart map, and I have a first coordinate for this point x. And I continue and I write x dim m of pi of x and I have already the first half of the coordinates, namely I project this down, and the first dim m coordinates of this guy are just the coordinates I would give to its base point by virtue of the original chart map. So far so good. But now I need to provide dim m further coordinates to not only say in which fiber it was lying, but to also know where in the fiber it was lying, right? So I need to provide further coordinates, and because the blackboard has come to an end, I need to change blackboards. But okay. So how do I do this? Now, well, maybe I this down a little bit so you can still see this. Aha. So how do we now go about this thing up there? Well, we could look at, consider the basis d by dx1 up to d by dx dim m. So this is the basis of the tangent bundle, but I'm telling you in a second, of the tangent space, I'm telling you in a second at which point. Look at this guy. This x is the original chart map that we were given from the atlas on M. And now for the x that I am given, I look at t pi of xm. I look at the tangent space to the point over whose fiber x lies, okay? Yeah? I look at this tangent space because, and that's the secret here, since the x lies in there, quite trivially. The x lies in the tangent space over its own base point. Clear? So I look at these guys, pi of x. Pi of x. This is a basis of this tangent space. But because this is a basis, I can take x and I can expand it as capital XA d by dxa at the point pi of x. Do you agree? For real numbers R. Each xa is an element of R. And the idea is quite simple. I choose now precisely these real numbers xa from this expansion. I choose precisely these numbers x1 up to x dim m, up to x dim m, in order to provide the other half of the two dim m many coordinates, and I coordinatized this point, I have a chart that's this orange domain pre-im pi of u, and this chart map xi assigns to an arbitrary point in this set of two dim m numbers. And that's a chart, and what remains to be shown that any two such charts, pre-image pi of u, xi, and pre-image pi u twiddle, xi twiddle, are C infinity compatible. And I will put this on the problem sheet. It's quite simple. And once you have that, you showed if M is a smooth manifold, you can inherit the smooth structure to Tm. And once you have that, you can talk about this projection map being smooth. And then you have a smooth bundle.